Question 5. Methanol, CH3OH, is an alcohol with many uses. Draw a diagram show how two methanol molecules interact with each other through hydrogen bonding in the liquid phase. Include all partial charges, that means delta pluses and lone pairs of electrons on your diagram. So the first thing you've got to do is draw two methanol molecules, so CH3OH, CH3OH, that's your first bit. Then each oxygen has got two lone pairs. Now you can either draw them like this, which is orbitals, or you can put two dots for each lone pair or two crosses for each lone pair. I usually do two dots, but these orbitals are fine, and there should be two on an oxygen there, and you can put two on this oxygen here as well. But it's the two on this oxygen that are most important here, and as long as you've got two lone pairs on this oxygen, then it doesn't matter if you've not got the two lone pairs on this oxygen. Then you need a delta plus and delta minus. Really there should be a delta plus and delta minus on this OH and this OH, but you don't get any marks for this one, it's just mainly this one. So as long as you've got two lone pairs on this oxygen and you've got an OH with the delta plus on here, that's fine, because it's this section here that's going to form the hydrogen bond. And the hydrogen bond is the dotted line. You need a dotted line, and that O, H and O should be in a straight line, because those two delta minuses, those two oxygens, repel as far as possible. And the dotted line should come from one of the lone pairs through to the H on the delta plus. So just to recap, draw the two molecules of CH3OH, put the OHO in a straight line, put lone pairs either by drawing orbitals like that, or two dots, two sets of dots, or two sets of crosses. You can put lone pairs on both oxygens if you want, but it's this main oxygen that gets you the mark, and delta plus and delta minus on this OH gets you the mark, although it's good practice to put them on here as well, and line it up OHO. The bond angle around the oxygen atom in methanol is slightly smaller than the regular tetrahedral of 109.5. Explain why this bond angle is smaller than 109.5. It's because you've got lone pairs, so a tetrahedral will be four bonding pairs, something like methane. But as soon as you put lone pairs on there, then the bond angle reduces. So if you had one lone pair, it comes down to 107, so it goes down by 2.5, 2.5 if you introduce a lone pair, and down by another 2.5 if you introduce a second lone pair and have two lone pairs and two bonding pairs, right down to 104.5. So what actually happens is it's due to the electron pair repulsion theory. So oxygen has two lone pairs, and lone pair repulsion is greater than lone pair bonding pair repulsion, which is greater than bonding pair repulsion. In other words, these two lone pairs repel the greatest, and then the lone pair to bonding pair repels next greatest, and then the two bonding pairs repel the least. So the two bonding pairs get pushed closer together. Methanol is made by a reaction of carbon monoxide with hydrogen. Carbon monoxide and 2 moles of hydrogen react in an equilibrium reaction to make CH3OH. Look, it's exothermic here, so it's minus 91. And look, there are 3 moles of gas on the left and only 1 mole of gas on the right. The reaction used a copper-based catalyst, a pressure of 10 megapascals and a temperature of 550 Kelvin. These conditions are used to provide a balance between the equilibrium yield, reaction rate and cost. Describe how use of a catalyst and change in pressure and temperature each affect the equilibrium yield, reaction rate and cost for 6 marks. So you've got to break it down. So how are you going to break it down? You're going to mention that that's negative. That means that going in the forward direction, i.e. the carbon monoxide and hydrogen making the methanol, it's exothermic and gives out heat in this forward direction. Therefore, if by Le Chatelier's principle you lower the temperature of the surroundings, then by lowering the temperature of the surroundings, then by Le Chatelier's principle it's going to oppose that change and try and increase the temperature. So by lowering the temperature, it's going to try and increase the temperature. How can it increase the temperature? Make more methanol, increase the equilibrium yield, or shift the position of equilibrium to the right hand side, because when you do so you make heat. So if you lower the temperature, then it's going to make more heat by shifting the position of equilibrium to the right hand side and make more methanol. However, at a very low temperature, the reaction rate is so slow it would take such a long time to reach equilibrium, so a compromised temperature of about 550 degrees C is used. So by using a higher temperature, that's going to increase the cost than using a lower temperature. Now there are 3 moles of gas on the left hand side, 1 carbon monoxide and 3 hydrogen, making 1 mole of methanol. So the gas on the left-hand side take up more room, so they've got a higher volume of the gases on the left-hand side. So at high pressure, by Le Chatelier's principle, the equilibrium will shift to the right to lower the pressure and take 3 moles of gas down into 1 mole of gas, because the volume's reduced and therefore the pressure's reduced. And so you can get a greater equilibrium yield, more methanol in other words. So a higher pressure gives a faster rate, more particles in a smaller volume, so more chance of successful collisions, and also a greater yield of methanol as the equilibrium shifts to the right hand side. Therefore a very high pressure, 10 megapascals, is used, and that's going to be costly. Creating pressure is costly. A catalyst is used to provide an alternative reaction route and lower the activation energy and speed up both forward and backward reactions, so equilibrium is reached more quickly. It's not going to change the position of equilibrium, but it is going to mean that you're going to lower the activation energy, and a catalyst usually saves on costs because you need less energy, because the particles need less energy to react, i.e. the activation energy is lowered.